Okay, so we discussed the abstract data type list, right? And so we showed how to insert, delete, and find. And moreover, we showed the implementation as a linked list. Now what we're going to do now is going to build on the linked list and describe implementations of other abstract data types. And sort of the most natural ones to go after a list and very important ones are the stack and the queue. So the stacks and queues basically support only two operations. Unlike lists which support insert, delete, and find, stacks only support effectively just inserts and deletes. So I'll sort of write this out over here. And so the insert in the stack is called a push, and the delete is called a pop. And in queues, so just let me adjust this. In a queue, it's called enqueue, and the delete is called a dequeue. Now the difference between a stack and a queue is basically, one can think of it in terms of the difference in the delete function. This is delete the newest element inserted, and this is to delete the oldest element inserted. So the only difference is that it's just insert and delete. You cannot find in a stack and a queue. And this is often called a LIFO, which is last in, first out. And this is called FIFO, which is first in, first out. Sometimes you will refer to stacks being mentioned as LIFO queues. There's a last in, first out queue or a FIFO queue. In this course, we'll talk about them as stacks and queues. So when I say stack, I mean LIFO. When I say queue, I mean FIFO, first in, first out. And so we will be doing over this lecture and maybe the next lecture is to really discuss stacks and stacks. And stacks are extremely important in actually understanding recursion. So this is, again, an abstract data type. This is just a specification. I'm just saying insert, or you have to implement the push and the pop. So in a stack, you can think of a push as insert element at the top of the stack, and a pop is to delete, or often it's to get the element. And this is where at the top of the stack. And if you recall, there was some discussion in class as to why my delete function was returning a node. And you'll see that that's because when you want to implement a stack, when you pop the stack, you actually want to get what's on top. So you remove it from the stack and you get it. And sometimes you'll see often a peek operation. And so peek just is get element at the top without deleting. The common ones are push and pop. Sometimes you'll see a peek. So this is what happens in a stack. And in a queue, so NQ, often they'll say insert at the end of the queue, and DQ is to delete at the beginning of the queue. So I'm just telling you what stacks and queues are so that you see the distinction between them and you understand what's going on. We will be actually discussing stacks in more detail. Queues will sort of maybe come actually later on in the course when we talk about breadth first search. Now, before I tell you about how to use stacks, let's just talk about how to implement a stack. So this is just a specification, and I now need to tell you how to implement this specification. How do you actually implement a class or an object that actually has stack, that performs a stack operations? Any questions at this point? Okay. Yes. Typically, yes. I should say that when you delete, you'll often return the element. And this is often what happens is, the way these data structures work is you're getting elements in some order and you want to process them in a different or maybe the same order. And so you can think of it as, often in a queue, like if you're actually, let's say, visiting a website and there are multiple people who visit, and then the server needs to decide who to send traffic to, it might insert everyone who visits in a queue and then process them in that order, if that makes sense. Now, what is not hard to see is that a stack can be implemented as a linked list. So push is to simply insert into the linked list. And remember that our insert adds element at the head. So this seems to work out exactly how we want, right? So if we think about this being our linked list, and if you wanted to push 42, the insert would simply create a new node with 42 and make the head point there. Right? So this in some sense seems to work out perfectly for push. How would you implement a pop? How would you implement the pop function? You just need to delete the head, right? So, I'm sorry, can you repeat that? You would need to move the head pointer, exactly. So you would need to move the head pointer, and you would just need to make that element, you would have to make this pointer null, right? And then you can return that element. Now note that this is already sort of encoded in the delete function that has been implemented. So you don't need to re-implement it. You can just write a function called delete head, which simply deletes the head and returns the old head, right? So pop is to simply delete the head of the linked list, right? And the peek function would simply return the head. So hopefully you can see that implementing a stack is pretty straightforward once you have a linked list. You can just actually represent your stack as a linked list. The push of the stack would simply insert into the linked list. The pop of the stack would simply delete the head of the linked list, and the peek function, if you need it, would just return the head. Again, this is, in some implementations have peeks and some don't. And so for that reason, I'm not going to give you a stack implementation because I think you already know how to implement a stack now, once you understand linked lists. Are there any questions about what a stack is and how to implement it? Yes. Not necessarily. You can also implement a peek by just doing a pop and then just pushing it back. Right? So you are not necessarily going. I don't think you will need to, but if you need to, you can just do a pop and a push. Okay, so yes. That's right. So you would delete and return the old head. But if you think about the delete function that I implemented, it automatically does that. Remember that it returns a pointer to the node that just got deleted. Right? And that's why the implementation of the linked list that I gave you has that functionality. That is usually the best thing to do, and this is, because in general, if it's not an int but an object, it's just convenient to return the node itself. And the reason is also, like, if you wanted to implement the peek as a pop and a push, then you could just delink the node and then relink the node if you wanted to do that. Although you don't need to. But in general, it's just convenient for us to talk in terms of the node itself. The implementation may do something else, but that's just it. I think just sort of mentally, it's helpful to think of you're just returning the node as is. Questions? Okay, so now let me tell you about a sort of canonical problem. A canonical algorithmic problem for which stacks are the best solution. And this is an important thing, for you to know. It's sort of common. It's actually it's not an uncommon interview question. And so let's look at this problem of checking parentheses. So let's just look at a sequence of parentheses and bracket characters, symbols. So this is correct. But this is wrong. Right? So this is a correct parenthetical sentence. This is an incorrect parenthetical sentence. And so your job now is to write a program or design an algorithm that, given a sequence of parentheses symbols, determines whether it is correct or it is wrong. Where do you think something like that comes up? And things like this come up every day. You are implicitly using such an algorithm every day when you exactly G++ or GCC has it. Or those of you who are familiar with HTML would know that HTML has these tags like head, right? And then usually you close. So HTML, XML, these sorts of markup languages often have these tags, right? And then within this you might have paragraph, so on and so forth. Yes? So think of it, HTML is a markup language. It's basically, well, I don't want to get into all of that, but a language which is, let's say, used to render some kind of text or to structure text. Let's just, I mean, that's not exactly what it is, but let's just think of that in this example. Right, so you basically put these tags around things that are the head or the title or a paragraph or a link, what's in italics, what not. And this is like a parenthetical statement where the kinds of parentheses, there are lots of different kinds of parentheses. And your browser, when it is rendering the text, has to parse the HTML. And part of parsing the HTML is to determine whether it's correct or wrong. I mean, of course, when it's correct or wrong, it has to do something when things are wrong. But you can imagine that the parsing of the HTML implicitly has to do something like this. Does this make sense? Okay. Let's start by actually a really simple algorithm. So suppose all parentheses were of the same type. So you just have this. Okay, so and you have maybe so on and so forth. And think of it as represented as a string or as an array of characters, just for convenience. And so in any pseudocode that I'm going to write here, I'm kind of, I'm going to be a little imprecise about the language. I'm going to write C style code, but I may call certain functions or certain, I might use certain, non-standard syntax just to make it simpler. So think of this as like, this is an array A of characters, if you will. What would be a very simple algorithm for this? Don't even think stacks. Don't think stacks. Simple algorithm for determining whether such a string is a correct parenthetical string. Correct. So if you have a closing before you have a starting, so this is wrong. But is this enough? There need to be an equal amount of opening and closing. But what if you had that? Now this example cannot happen, but this is coming sort of later on. This has equal number of open and close. Good. So the number of closing brackets never exceeds the number of opening brackets. Okay, so let me verbally say this and I'll write this down. So maintain a counter that starts at 0. Every time you see an open, increment the counter. Every time you see a close, decrement the counter. Okay, so when you see an open, increment the counter. When you see a close, decrement the counter. And now, how do you determine, just using the counter, whether this is correct or not? The counter should not go negative, exactly. So if the counter ever goes negative, then you can say the string is incorrect. And is that enough? Is 0 when it finishes. Right? So let me write out sort of the pseudocode. So you maintain a counter that goes to 0. And I'll say for I, I'm going to kind of use almost a Python type syntax, 0 to the length of A minus 1. Okay. And I'll say if A of I is opening, count plus plus. If A of I is closing, count minus minus, and I should add this extra condition in here. I'll say if the count is less than 0, then you can output wrong. And finally, we'll just say if the count is greater than 0, output wrong, else output right. Right, so this is a very simple algorithm that works for counting parentheses or for checking whether a string is a correct parenthetical string when you have only one type. And this is by maintaining a counter. It's a very simple algorithm that maintains a counter. It's a single for loop. This seemingly has nothing to do with stacks or data structures or anything, but this is a good trick to know. Okay, so any questions about this? Any questions, any doubts? Yes? That's exactly what will happen over here then. If there are too many closings, then it's going to keep decrementing the count, and eventually the count goes negative. Yes? No, so in this example, you mean? So what would happen is that it would, as soon as it starts, the count is initialized to 0. And as soon as it sees the very 0th character, it's going to decrement the count. And then it's just going to output wrong. Within the loop, yes, exactly. Checking within the loop. Yeah, exactly. After every symbol, I'm checking if it goes negative. Yeah, which is why, I had to move the closing parentheses, the curly brace there. Right, exactly. Okay, so hopefully this is clear. So what about multiple parentheses types? And a first guess is to maintain a counter for each different type. So this is like a first guess. It turns out this doesn't work, and I'll give you a simple example where it doesn't work. So if you have a situation like this, then the normal parentheses form a correct statement by themselves. The square brackets form a correct statement by themselves, but they're interleaved the wrong way. And therefore, if you maintain a counter for each different type, that's not enough. Right? You could just imagine doing the previous algorithm with a separate counter for each type, but that doesn't work. Yes? So what you're saying is you could try to keep track of the different counters and how they relate to each other. So you could potentially figure something out for 2 counters, but now let's say there are multiple different types. And now you need to sort of keep track of, which is the one that you compare first. If you check for adjacency, it would work, but adjacency is not the only, I mean, okay. That's no, but what you could have something like this, where once you come to this point, you come to there, the square brackets is still going to be non-zero, but this is correct. So the problem is, and someone had mentioned, that the adjacency seems to help. Like there's something about things being adjacent, that a closing should never be adjacent to a different opening. And this is exactly the kind of information that is very easy to track using a stack. So let me tell you the solution, the algorithm, a very simple but very elegant algorithm that uses a stack. And this is actually where stacks come up a lot in parsing. Again, I'm going to write this out as pseudocode. So I'll say start with an empty stack S. So S is an empty stack. And I'll say for I going from 0 to the length of A minus 1. Remember, A was the input, right? We thought of it as an array of characters or a string, whatever have you. So I'll say if A of I is open, then I'll just say S dot push A of I. So you're going to push it onto the stack. If A of I is closed, is a closing. Okay, so if A of I is closing, now it becomes interesting. I'll say let C be equal to S dot pop. So let me pop. And if C and AI don't match, then just output wrong. Finally, I'll say if S is empty, output right, else output wrong. So that's the entire algorithm. So let me say this again. If it's an opening symbol, push it onto the stack. If it's a closing symbol, pop the stack and check if it matches with the closing symbol that you're currently looking at. And if it matches, then just go on. If they don't match, then immediately output wrong. And at the end, the stack should become empty. And you can see the stack should become empty because for every opening, there needs to be a closing that matches. So for example, if you look at, in this case, what is going to happen is, you see the symbol, that's going to be the stack. You see this, you're going to push this onto the stack. So let me just draw the stack down here. That's what the stack is going to look like. Now you see a closing symbol, but this, when you pop, you get the square bracket, and yet the current symbol is, the normal parentheses, so you immediately output wrong. In this case, if you look at what the stack is doing, it's going to push this, push this, push this. then that is going to match up with that. They pop. This closing parentheses is going to match with this opening parentheses, and they will pop, and this will pop. And finally, this closing square bracket is going to match with this closing square bracket, which gets popped, and the stack becomes empty. Okay, so this is the algorithm, the basic algorithm, to use a stack for matching parentheses. Any questions about this? Go ahead. Any number of types it works. And if you think about it, because there's nowhere that you're maintaining any counters, you're just maintaining the stack itself is just going to contain all different types. What's nice about this is you don't even need to know before the algorithm runs how many different types there are. For example, if you're parsing an HTML file with tags, and even if someone came up with custom tags, right, you can just do this in one loop over. This is one of the most classic use cases of a stack, so it's important that you know this. If there's nothing else you take away from today's lecture but this is still useful. Stacks are the canonical data structure used for dealing with parenthetical statements. Okay, and remember this fact, it's often asked in exams or tests or interviews that you have this parenthetical statement, what do you do? And the answer is you use a stack. And this is the algorithm. Yeah, the palindrome. It's a good question, but you're not allowed to use stacks. I said for that you can't use extra data structures. Otherwise, yes, you could. You have to be a little careful that you wouldn't be able to use this because you don't know what the total if you look at this algorithm, it doesn't know what the length is at any intermediate step. So it doesn't know when to start popping things off the stack. If you're looking at a palindrome, you have to match the first one to the last one. But in a parenthetical statement, for example, in a situation like this, you don't match the first to the last. You actually match this to this. Right? So it's a little more complicated, but there are similarities between those, and we'll actually go over. When we talk about recursion and stacks, you'll see where the similarities come in. All right. Any other questions? Sorry, there were two questions. So yeah, go ahead. Who came up with that meaning with this? It's a good question. I don't know if there's a good citation for this. It might be folklore, meaning that it's just been there. It's a good question. So more like modern parsers will kind of parse as they do this. They will parse while they're going along. So they won't go check and then go back. Modern parsers are sophisticated enough that while they're doing this matching, they're also parsing the text, if that makes sense. Right? So it doesn't necessarily have to go back. But fundamentally, there is usually a stack that is there in, when they're parsing, there are a couple of stacks maintained for various structures. So think of it more as, instead of thinking of this loop for this purpose specifically. The way to think about it is when you're parsing, as you encounter a new token, you'll have a couple of stacks. You might push them onto the stack or decide to pop the stacks. And you may be maintaining multiple stacks to maintain sort of multiple things. But I guess the point that I want to get across is the stack is the fundamental data structure used when you're parsing in this form. Yeah, and it's not necessarily the case that you would, like, if you kind of think about it carefully, you can do that without sort of going and checking integrity first and then going and parsing. But you're right that is another way of doing it. Like if you just wanted to quickly check, are the tags matching up? Yes. I'm sorry, your voice is a little faint. Go ahead, yeah. Correct, yeah, whether they match as a type, you're right. So I should say that they don't match as a type. So C should be opening, and this should be closing, both of the same type. Right? So that's what's going on. Okay, so hopefully, you learned something that was interesting. And now I want to sort of proceed to maybe what I consider sort of most important part of today's lecture. And this is something that is going to be useful both for your second test and your second assignment. And that is stacks and recursion. Stacks and recursion. So I'm going to sort of make a general statement that any code that uses recursion can be converted to non-recursive code, that uses a stack. Meaning stacks can be used to simulate recursion. And actually, in some sense, it's almost the other way around. Recursion is implemented using stacks by the operating system. So recursion is implemented through stacks. And if you've ever heard of the term stack, the call stack, and you've obviously heard of what Stack Overflow, you've heard of the website, and that's actually related to recursion because recursion is implemented through stacks. And what we're going to see is I'm going to teach you how to do this process. How do you convert recursive code to a stack-based code? And in your second homework, I'm going to give you a more complex problem that can be solved with recursion and say, solve that problem using stacks. So let me begin by describing a simple recursive algorithm. And the reason I'm doing a simple recursive algorithm is so that we can actually sort of unfold it completely, and then we'll see what's going on with the stacks. So I'm going to write a function called print reverse. Okay, print reverse. And let's just say, it takes as input an array. And it just prints the array in reverse. That's what it does. Now you can obviously implement this by a for loop, just printing an array in reverse, printing the ints. I'm going to give you a recursive piece of code that does the same thing. And then we'll see how to implement that through stacks. So remember, if we're doing recursion, we're actually going to have some, I'll say int I. So I'm going to write a recursive function, and then there will be a dummy call to this with sort of the appropriate, parameters. So this is going to be, these are going to be indices in the array. And this function is just going to print the portion between I and j. It's going to print the portion between I and j. Right? So firstly, I'll say if I is greater than j, then just return. Right? Because that doesn't make sense. This is just for safety. I'll say if I is equal to j, this is the base case, then I'm just going to write it out in one line over here so that I can conserve space. I'm just going to say print the character AI and then return. Right? This is the base case. You should never write code like this. I'm just writing it this way because it's on paper and I want you to be able to see everything. But this is the base case. This is just to check parameter safety, just to be on the safe side. Okay, now I'm going to make two recursive calls. So I'm going to call print reverse of A. I'm going to take I plus j divided by 2 and take the floor. Okay, I'm going to take the floor of I plus j divided by 2. Again, I'm writing this in mathematical notation. In code, you could basically, you can take the floor and ceiling, or you could just say, typecast it as an int. You can do this in multiple ways. So what I'm saying over here is, if you look at this recursive code, it's supposed to print everything between I and j. It goes to the middle. It takes I plus j divided by 2. It takes the floor of that. And then it makes a recursive call for this part, then a recursive call for this part. So it does a recursive call here. Then I'll say print reverse of A, I plus j divided by 2. And then return. Okay, this is my recursive code here. So what is the recursive code doing? It says first print the portion from the midpoint to the end in reverse. So print this part in reverse, then print this part in reverse. So I'm going to pause now, take any questions on this. I want to make sure that you understand what this recursive code is doing and how it works. So let's talk about, good question. Let's talk about the dummy call. So when you want to initially call this, you could call print reverse A. You do 0, and then the length of A minus 1. Right? That's how you would initially call this function. The recursion is happening here. If I was 0 and j was 100, then I plus j divided by 2 would be 50. So you're essentially going to print from index 50 to index 99 or 100, depending on whether it was length 100 or 101. So this would be either 49 or 50. So you go from there to the end, and this call does it from I to that point. Good question. So suppose you didn't make that recursive call. Suppose you didn't make that recursive call. Then what would get printed? Okay, I want you to think about this. I'll pause for a minute. So this is your piece of code now. And tell me, what is this going to print? And let's say you made this was the initial call. What is going to get printed? Good question. A of j, just the last character, or in this case, a of length minus 1. Just the last character. If you make only one recursive call, it's only going to print the last character. Why? Because each call makes a recursive call. This recursive call is going to go here and make another recursive call. The only thing constant is j. And this argument is just going to keep increasing. It's going to keep increasing until they both become the same. And then it's just going to print that in return, and that's it. So if you make one recursive call, it only prints the last character. You make both recursive calls and it prints everything. And it's important that you be careful with the indices here. It's very important that we understand this piece of code before we proceed. And so towards that, what I'm going to do is I'm just going to take a poll. And my question is, okay, so there are three options in this. It's RGB. So the first option, that's R, is I understand this code. We can proceed. The second option is I don't understand, and I'd like to see you work out an example. Okay? So the first option, R, is I understand the code. And the second option, G, is that I don't understand the code. Could you go through an example? And don't do B, like don't do the last option. Okay, so it seems that there's a fairly reasonable cohort that would like me to work out an example. So I'll go ahead and work out an example with this code. So thanks for the poll. Speaking of polls, I also put a poll on Piazza about how familiar you are with Unix tools and makefiles. And please do fill out the poll if you haven't. It's useful information for me and for subsequent instructors so that we can prepare this course appropriately. Or we can adapt this course the next time around, and also for me to know this time. Okay, so I'm going to go ahead and work out an example. And I'm going to start with a relatively short running example, which will be convenient for us. Okay, so, and just to keep it simple, my array is going to be 0, 10, 20, 30, 40, and 50. That's what the array is going to be. Okay? And so what do you want the output to be? The output should print 50, 40, 30, 20, 10, and then 0. And that's what should be printed. So let's go ahead and see if this prints. So this index is 0. This is the index 1, index 2, index 3, index 4, index 5. So the first call is going to be print reverse. I'm just going to call it print rev, just to shorten the amount of ink being spent, to reduce the amount of ink being spent. And initially you're going to call print reverse 0, 5. Now I is not greater than j, so this is not going to happen. I is not equal to j, this is not going to happen. Remember, I and j are 0 and 5. So now it's going to make two recursive calls. So I'm just going to write this out over here. So here's the first recursive call. Okay, can someone shout out what those arguments are going to be? What are the arguments of the first recursive call? Remember, I is equal to 0 and j is equal to 5. So 3 and 5. right? 3 and 5. And what about the other one? Zero and 2. So by the way, you may want to write this down. Just write down these two calls, and that way it'll be a lot easier, so I don't have to keep moving the paper around. So I'd recommend that you just write down just these two lines. Just write down those two lines, right? So that you know which order they're being called and you know what the ceilings and floors are. Okay. Now, which was the first call? This was the first call, right? So this is going to run now. Remember, so now this is I and this is j. I is not equal to j, nor is I greater than j. So this is going to make two more recursive calls. Okay, what is the first recursive call that this makes? What are the parameters? Sorry, I didn't get that. It's 5 and 5, right? Because 5 plus 3 is 8 divided by 2, which is 4 plus 1. So 5 and 5. And what about the other call? Three and 4. But note that at this point, this call made this call. I'm just writing this down for convenience. But this call called this 3 and 5, which called 5 and 5. Okay, so once it calls 5 and 5, this is the base case. I is equal to j. So it's just going to print AI and return. So this is going to print the fifth element. So let me just write out what is being printed over here. So this is the printing. So it prints 50. This is going to print 50. And then it returns. Now it's going to make this recursive call. This is going to make a recursive call print rev a 4 and 4. Right? So 4 plus 3 is 7. 7 divided by 2 floor will give you 3 plus 1 is 4. So it's going to print that. This is now the base case. So it's going to print what is there in the fourth element of the array, which is 40. So it's going to print 40. Then it's going to go back. This is going to make another recursive call. Remember, this is not the base case. This has to make two recursive calls. So it's going to do print rev a 3 and 3. That is going to print 30. This goes back. So both recursive calls are done. Both recursive calls are done. So now it's going to return. This code is going to return. It's going to return. Both of its recursive calls are done. That's going to return. Now this is now going to make its first recursive. So now it's going to go down here. So print reverse of a 2, 2. Right? Because 2 plus 0 is 2, divided by 2 is 1, plus 1. That is now going to print 20. It's going to go back. And then there are going to be two more recursive calls here. So this is going to be print reverse a 0, 1. And this will make two more calls. And eventually you'll see that it's just going to print the output. So is the process more clear now? I'm just going to relaunch the poll. First option is yes, this is clear. B is, R is yes, this is clear. G, the second option, is no, I'm still confused. Okay, good. I think most of you seem to understand what is going on here. So this picture is really useful. Now let's think about how is this actually getting implemented. How is this getting implemented? And the implementation is actually done through a stack. Okay, so now let's kind of walk through this process a little carefully. I want to redescribe this process, which was done through recursion. Instead, I want to do it using a stack. And I want to look at what the call stack is. So under the hood, what is going on in the operating system? So let me zoom out a bit. That way we have the entire picture here. Okay. So I'm just going to move this, reset things a bit here. So what I'm going to do is I'm going to maintain a stack here. Think of this as the call stack. And the important thing to maintain is what I and j are. Okay. So I is equal to 0 and j is equal to 5. This is what happens initially. This is what happens initially. So I is equal to 0, j is equal to 5. This makes two recursive calls. This makes two recursive calls in this order, right? So first recursive call is I plus j divided by 2 to 1 and j, and the second recursive call is I plus j divided by 2. Over here we can see this is the first recursive call, and this is the second recursive call. Right, this is the first recursive call, this is the second recursive call. Now I'm going to implement this by saying, okay, so now to deal with the first call, I'm just going to pop, this is a stack now. I'm going to pop the stack, and I'm going to push in the recursive calls. For those of you who know what tail recursion is, this has tail recursion, and that's why I'm implementing it this way. So I pop the stack. So stack now becomes empty, and I push in the recursive call. So what are the recursive calls? It's this one and this one. Except I push in the second recursive call first. So I push I is equal to 0, j is equal to 2. So think of this as pushing pairs. I'm pushing the arguments onto the stack. I'm pushing the arguments onto the stack. And this is going to be I is equal to 3, j is equal to 5. Okay? Okay, now I'm going to go one step further and say now I'm going to look at the top. So I'm going to pop I is equal to 0, j is equal to 2. So I just pop this, and I'm going to push in the recursive calls that this made. So it made 3, 5. So it makes two calls, 5, 5, and 3, 4. So I'm going to push the pair. So I think of it as pushing a pair. I'm pushing the pair 3, 4, and then I'm going to push 5, 5. Remember, I pushed the second call first. So I is equal to 3, j is equal to 4, and I is equal to 5, j is equal to 5. Now I pop, but this is a base case. So there are no more recursive calls here. So this is base case. So I can go ahead and perform the operation of the base case, which is now print. So I'm just going to print what is there. So I printed, in this case, I printed 50. So all I did was a pop. So if I pop and I hit a base case, because I have to push in the recursive calls, but there are no recursive calls. So I is equal to 0, j is equal to 2, I is equal to 3, j is equal to 4. So I have popped that, and I'm back out. And so what happened here was that basically I looked at these recursive calls, I found this, I popped it, and I'm done. So now I go back to this one, which is what is happening in the stack because you pushed in 3, 4 before 5, 5. So now let's look at 3, 4. Again, we're going to do a pop. And just to show you what's going on. So 3, 4 makes 2 calls to 4, 4 and 3, 3. So I push 4, 4, then I push 3, 3. I'm sorry, the other way around. My apologies. I always push the second call first and push 4, 4, right? So I still have I is equal to 0, j is equal to 2, right? That's already there. So the stack remembers that you haven't finished this one yet. So it's going to finish all of this before it gets to that, which is exactly what you need to do in the recursion. You need to deal with this recursive call. So now we push in the recursive calls for this. So I is equal to 3, j is equal to 3, I is equal to 4, j is equal to 4. So now we're going to do a pop. That's a base case call. So you print, so you go ahead and print the 40. And then you do another pop because you keep popping when you see base case calls. So there will be a pop and there's another pop and that prints the 30. And now we're down to I is equal to 0, j is equal to 2. So you see how basically this is the call stack. And you see how the call stack follows what the recursion did pretty much as is. I'm going to write this out as code. But I want you to understand this picture. So any questions at this point? I'm going to be really surprised if there are no questions at this point. Good. So there are lots of people who had questions. Good. Yes. So maybe it might be better if you raised your hands, and then you know the LSS tutor will just call on you one by one. So Mohammed, you can just call on them one by one. Exactly. So you actually jumped ahead. That was one of the questions I was going to ask. If you flip this order, then you would just print it in order. Right? And because what that does is if you look at this tree of recursion calls, it's just going to flip each of these, and that's just going to flip the entire order. Exactly right. Mm. I mean, this is just a specific recursive implementation that I gave you. Right? You could do it in multiple ways. You could even make this like I plus 1, say. And the reason I did this is I just wanted to give you code that looked a little different so that we can go through this example. This is more of a pedagogical tool rather than the way that you would actually code up a print reverse. So if you just call print reverse of I to j, then it'll go in an infinite loop. It'll never go down to the base case, right? You have to get I and j. Okay, so maybe I understand your question now. When you make recursive calls, think of the difference between I and j. That difference has to keep decreasing in the recursive calls, otherwise it'll go into an infinite loop. And that's what these calls are doing, right? They're basically reducing the gap between these arguments. Does that make sense now? The gap has to keep reducing between the arguments I and j. So okay, I haven't finished the process. I haven't finished the process. So you're right that, okay, so now I need to basically deal with this. So I'm going to pop the stack and push in the recursive calls. The recursive calls for 0 and 2 were 2, 2, and 0, 1. So those are going to get pushed in, and eventually you'll pop those out. Does that make sense? So I haven't finished this process. I didn't finish it, but I think that it's basically just working out exactly what I did over here. You pop the stack and you push in the recursive calls. No, this is not inside the recursive calls. The way to think of this is a way of simulating the entire recursion through a stack. So I'm going to give you more specific code in just a moment to show you how all of this is done. One way to think about this is what the operating system is doing. Like if you think about recursion, how does the operating system know which call you're dealing with? It's keeping track of everything using a stack. Exactly. So I'm sort of showing you the stack of recursive calls. And then I'm now going to tell you, but then you could implement the stack. Instead of letting the operating system do it, you could implement the stack yourself. And then that way what happens is you sort of deal with the recursion at your own end, which often leads to faster code because, recursion can be expensive in terms of the operating system, and you can actually simulate it entirely using a stack. Yeah. Questions? So good question. So this is where remember the stack is last in first out, right? And that's why you have to sort of switch the order. Because in terms of the code, it's kind of the code is in some sense first in, first out, right? The code is what is the first recursive call? That's this. Then what's the next recursive call? That's this one. But when you're doing it in the stack, because the stack is last in, first out, you have to flip the order. So recursion, I mean, you're right. So and actually in some recursive situations, you need to make many recursive calls. And you will see examples like that in questions that I'm going to give you. So in this, and it depends on sort of how you're conceiving of this algorithm, right? So what this is doing is in saying one way to think about reversing a large array is to break it into the first half and the second half, reverse the second half, then reverse the first half. So if you heard my logic, I was effectively calling the recursive procedure twice because I have to reverse the second half, then reverse the first half. So the logic fundamentally has two recursive calls in it, and that's why you have this. You have two recursive calls in here. Yes, you will need to figure out how many recursive calls are being done. Yes. And indeed, sorry, go ahead. Yes, you will all put exactly. The more recursive calls there are, the more you're going to be pushing onto the stack. Exactly. I'm sorry, your voice is a little faint. Could you increase the volume? Yeah. Yes. You should draw the diagram for small examples. I think actually that's the way to go about it. Draw the diagram for small examples to make sure that you understand what's going on. I would completely recommend drawing, yeah. So actually the best will be working on examples, and I'm going to give you a bunch of, for the second test, I'm going to give you a bunch of example functions to code up recursively. And I think like just thinking about those should probably help you. So I'll give like 3 or 4 examples, and I'm also going to give you a recursive piece of code. I'm going to share with you a Codio box with some recursive code. Okay, so maybe one more question before I continue with the lecture. In this situation, there is no reason to, you'll do it iteratively, but I'm going to show you examples where you're not going to be able to write iterative code. That's a good, yeah. So usually you would use recursion in lots of cases, and we're going to see this. There's going to be backtracking algorithms that sort of make choices and then backtrack their choices, where recursion is much more natural, where it's not easy to write a loop that's going to generate things. And indeed, okay, so that's a good segue onto what I was going to do. I'm going to talk about a problem where you're going to have exactly that. So we have, at this point, we have about 15 minutes left, which isn't a huge amount of time. So what I'm going to do is I'm going to really quickly just write out the print reverse that I described using a stack-based implementation. And I'm going to do this I want to write this out quickly so that you have this in the notes and you have it in the lecture. I'm not going to answer too many questions about it because I'd like to move on to something else. So, but hopefully this will sort of explain things for you. So I'm going to write the print reverse. In I, and I'm sorry, so we'll just take another integer parameter called the length. So this is just going to simulate that entire procedure that I described using a stack. So let's create a stack S, and I don't want to deal with the specific objects right now. I'll say this is a stack of pairs. So you'll have to create a pair class and you'll have to sort of template it. Let's not worry about that. I have examples in the code. I'll share examples of code with you. So, or I'll say stack of pairs. And then I'm just going to initialize something called a pair called top. And then I'm going to initialize an initial pair. Now I'm going to set init. I'm going to write this out almost in like a Pythonish language. Just write this length minus 1. So this is my pair. And then I'm going to push this pair onto the stack. So this is how I start the stack. This is exactly doing this process here. right? So this is what I'm pushing onto the stack is the base, is like the dummy, or is actually the head recursive call, the first recursive call. So I'm pushing 0, length minus 1. That's what is pushed onto the stack. And then I'll say while s is not empty, the top, I'm just going to pop the top. I'll say if, okay, so let me just define an int I is equal to the, think of it as the first element in the pair, and int j is the second element of the pair. So I'll say if I is equal to j, then you could print AI and return. This was the base case. Otherwise, I push I and I plus j divided by 2, and then I push I plus j divided by 2 plus 1 and j. So I'm pushing pairs onto the stack. And this is like the entire description. So I've just redone the recursion using a stack. So I have described that picture using a piece of code. Now I've written this code. Unfortunately, I don't have time to answer questions about this code, but hopefully it should be clear if you understood the previous picture. And you have this, I will scan it and you'll have access to it. What I want to talk about is really to answer the question that was asked before. So what is an example of a function or a method or an algorithmic task where it's not obvious how you do it with iteration? And let's look at this, which is printing all subarrays. So if A is an array, let's say an array of ints, a subarray is an array with a subset of elements in the same order. This subset is not necessarily contiguous. So you could take this element, and this element. And these three form a subarray. Okay, now let me ask you a question. I'm going to poll you. If A has length n, so there are n elements in this array. There are n elements. How many subarrays does it have? Going to your discrete math knowledge, so the red choice is 2 times n, the green choice is n factorial, the blue choice is 2 to the n, and I'm just going to start this poll right now. So answer this question. If A has length n, then how many subarrays does it have? How many subarrays does it have? Is it 2 to the n? Is it n factorial? Or is it 2 to the power n? Okay. So the answer is not n factorial. N factorial is the number of permutations of the array. This is not a permutation. The elements have to be in the same order. The answer is 2 to the n. And why is it 2 to the n? Because it's basically, think of it as all subsets. For every subset of elements, you get a subarray. At this point, I will take questions. I want you to understand this. Yes. Yes. No. 1, 4, and 5 are in the same order. Right? I said it doesn't have to be contiguous. Contiguous means that you have to take everything in between. Does that make sense? Right? Yeah. So it's a subset of the elements in the same order. Okay, so is this clear? It's 2 to the n. Yes. Because permutations means take all the elements and put them in all possible orders. This is saying take a subset but keep them in the same order. You take all sets, just take all sets of elements and just write them out in the order of the array. Right? So this will give you 2 to the n. Okay? And let me give you a simple example. So let's say my array was 7, 101, 42. What are the subarrays? So there's the empty subarray, which has no elements. Right, there's the empty subarray. There's all the individuals, but let me write this out slightly differently, right? So I can say I could take the empty subarray, then I take 7, I take 7, 101, I take 7, 42, 7, 101. 42, and then I have 101, 101, 42, then finally I have 42. How many do I have here? 8 total. Let me just move this down to the end. 8. This is 3, and the number of these is 2 to the 3, 8. Okay, now here's your problem. Write a program that prints all subarrays. Write a program that prints all subarrays. And you'll see that, I'm sorry. Yeah, go ahead. Just do it. Initially, the question is just do it. Eventually, it's to do it using a stack. And what we'll see is, I will give other examples of programs that I want you, but you'll see that the most natural way to do this is through recursion. It's very hard to write a loop-based program to do this. It's not even obvious how you would write this using for loops or while loops, unless you use a stack. Because note that there are 3 elements, but there are 2 to the 3. There are exponentially many. There are exponentially many subarrays. And whenever you have something that typically requires exponentials, recursion is the way to do it. I've written this in this way to show you something. I'll write this out, and then you can go back and you can look at it, and you'll see. How do you actually go about writing a piece of code that would print all subarrays? Well, you say that all subarrays, the set, or I should maybe instead of set, let me use family. But family also means set. I'll say the family of all subarrays can be partitioned into two subfamilies. And again, family and set means the same thing. I'm using family here because I don't want to use the word set. So the first one is subarrays of A going from 0 to length minus 2. And the others are the subarrays that have the element A of length minus 1. Okay? So you can think of this, these are the subarrays that don't have this element. Those are all subarrays of A going from 0 to length minus 2. And then you have the subarrays that have this element. Does that make sense? So you can partition the family into two subfamilies. And you make a recursive call to print these subarrays and to print these subarrays. So there are fundamentally two recursive calls, each of which make two recursive calls, so on and so forth. And this will actually also give you the 2 to the n. Now we're nearing the end of the lecture, and I don't want to. I think it would be a bad idea to launch into this in the last 3 minutes. So I'll stop here, and the next lecture will come, and I'll discuss the recursive code for this problem. And I will want you to convert it to a stack-based code, and I will give you this implementation. But I want to first discuss the recursive code for this procedure, for printing all subarrays. And I'll do this at the beginning of the next lecture, maybe the first 15-20 minutes or so. Sure. So I can explain this once more. So here's your subarray. So let's just say there are lots of different elements, and it ends with 42. Now I'm going to break all subarrays into two groups: those that have 42 and those that don't. Those that have 42 are in the second part. Those that don't have 42 are really subarrays of everything going from here to length minus 2. Does that make sense? No, you don't have to do this for every element. The recursion will take care of it. If you recursively do it, it will take care of it. I'll do these recursively. Yes. Exactly. Sure, just give me 1 second. So I'll just end. So I'll end the lecture here. I'll take questions, and then there will be the announcement.